I left off yesterday with a bunch of theory and not giving you any examples, but today I'm going to sort of give you some more examples and tell you what the things I was telling you about yesterday are good for. Where I stopped, I was talking about Stiefel-Whitney classes. These are kinds of characteristic classes. So they're invariants of vector bundles, and they lie in the cohomology of the base, okay? And I had listed the properties, and I put them back there so that you could look at them while so if I say something and you're like, oh, I don't remember that, you can have a reference, okay? So, and one thing that I will say also maybe on this board is, so I said last time that we can write the total Stiefel-Whitney class, so you just write W without a subscript of your bundle as this formal sum, okay? And also, if M is a manifold, a smooth manifold, then you have then you have the bundle Tm over M, and we're going to write W of T of, so when I write W of M, so W of the manifold, I mean W of the tangent bundle, okay? Make sense? Okay. And I left also with an exercise. And so suppose that you have a trivial bundle, so you have Rn times X over X. And I'm going to be writing my trivial bundles by epsilon today. Epsilon, or sometimes, I don't know, maybe, yeah, so by epsilon. And, you know, by epsilon, I mean maybe if I want to highlight the dimension, I'll write epsilon sub n. Okay, these are just going to be my trivial bundles. And you can compute that the total Stiefel-Whitney class of epsilon is 1, okay? And maybe the hint / the solution is to consider the map of X to a point and pull this back. So trivial. Let me just say a hint. Look at the map from X to a point and put an n-plane bundle on the point. Okay? What's this? Yeah, those are both epsilons. Yeah, so equals to epsilon n. You're right, though. No, this is important. In mathematics, calligraphy makes a difference. But I think it's safer to just call them both the trivial bundle, because I will alternate. Yeah, okay, great. So, and so finally, we also had another thing that sort of showed up during all the talks is, suppose that you have an immersion of a manifold into, so M is going to be an n-dimensional manifold. And suppose that you have an immersion, then you can form so you have, there's a bundle called the normal bundle. So this is the normal bundle. And it's a k-plane bundle, right? So that lives over M. And if you look at the tangent bundle plus the normal bundle, well, that's the tangent bundle of R n plus k. And that's an epsilon n plus k. Yeah. Okay? So that's a trivial bundle. So if you took the total Stiefel-Whitney class of the sum of these things, well, if you're trivial, you're 1. So that's going to be 1. Okay? But you can... Sorry? No, I'm just saying, like, take an immersion. And, you know, it's an n plus k, okay? And I'm saying the normal bundle is going to have dimension k. Okay. Yeah, that's all, yeah. And then, but if you use the product formula, you get that this is the product of these total Stiefel-Whitney classes, and that's 1, okay? And so we're going to let W bar of, and okay, so I said the total Stiefel-Whitney class of Tm plus V is the product of this, but that's just, you know, I said earlier, if I put the tangent bundle, I'm just going to put the manifold in there. And W bar of M is going to be, by definition, W of the normal bundle for that inclusion, okay? And the way I'm writing it, it looks sort of like if it's independent of the nu, because on this side, the left side doesn't depend on the embedding. But if you pick k large enough, then the point is that this formula here is sort of telling you like a formal inverse of the Stiefel-Whitney class of M in the cohomology of the manifold M. And the cohomology of the manifold vanishes if you're bigger, or if your dimension is bigger or equal to M. So that this, formula is going to be sort of fixed, okay? You can actually just play in the cohomology ring and figure out, if you know what Wm is, what the inverse has to be, okay? All right, so let's see. I want to do, as long as you're immersed, yeah. You're right. Yeah. Okay, so let's see. Examples. So I'm going to need these, and I have to set up some stuff for Dylan too, and it's going to be nice to try. So I'm going to go through some stuff, and then I'll get back to Cobordism. Okay. So you have the tautological line bundle. I don't know how we're sort of denoting it, RPN. Okay. I think that for now, I'm going to talk about different ones. I'm going to write, so if I write gamma 1 over RPN, I mean the tautological line bundle. But if I put n, it's because I have more than one RPN around, and I want to remember where I came from, okay? So we want to sort of look at the total Stiefel-Whitney class of this thing, okay? Well, that's W0 plus gamma 1n plus W1 of gamma 1n, and there's nothing else because this is a line bundle. Right? Okay, dimension 1. But there's an inclusion of RP1 into RPN, and I have gamma 1n here, and it pulls back to gamma 1, which is this gamma 1, so gamma 1, 1 here. Okay? And you know that W of gamma 1, 1, so maybe you have I star, W of gamma 1, 1, well, it's W of the pullback of gamma 1n. But that pulls back to a W of gamma 1n. Okay? That's not 0. So that can't be 0. Okay? So this guy here, that's an element of H1 of RPN. And it's not 0. Okay? Make sense? Okay. So for any n, and this works for RP infinity too. Tautological bundle of RP infinity, you always get the formula, okay? So now let's finish. W0 is 1, and then we have the generator. And I've been calling it W1. Now you know why. Remember cohomology of RPN is Z mod 2, and I've been saying W1 modulo W1 to the n plus 1. Okay. And that's why I was calling that guy W1, because it's sort of this canonical first Stiefel-Whitney class. Okay. Great. Okay. I want to do one more example. Okay. So we're studying RPN. Throughout my talks, there's been these themes of these real projective spaces, right? So I told you the Stiefel-Whitney class of one bundle, but the one we're really interested in is the one associated to the manifold, okay? So the total Stiefel-Whitney class of the tangent bundle of RPN, okay? So how would you compute that? Well, before you can compute this, you have to sort of understand a little bit more what this tangent bundle is, okay? So I'm going to talk to you about what the tangent bundle of RPN is, and then we'll use that to compute the formula for this guy, okay? So let's see. Okay, so here's a little animation that I got from Dylan. So if you have a manifold, so M, and you're looking at the tangent plane, well, what's the tangent space? It's little directions in which you can move along M, okay? But now if we're RPN, what is that? Well, an element is a line L in Rn plus 1, right? Okay. So if I want to move my line around, I have to tell you where to send it. And the options are another line in Rn plus 1, right? So that's how I move a line. I send it to another line. Okay? So how much can I move? So I'm going to look at the linear homomorphisms from L to Rn plus 1. So I'm going to send L to another line in Rn plus 1. Okay? And so that's going to surject onto the tangent space of Rpn at the point L. Okay? But, you know, at the tangent space, the 0 is the don't move. So if I told you to send the line to itself, then you haven't moved around in your tangent space. So that shouldn't be accounted for. So that should be in the kernel of this map. So these are homs R from L to itself. Okay? Now, we're looking just at one point, but let L vary. Okay? I'm saying it's a short exact sequence, yeah. So I'm saying this map is surjective. And what's the kernel? What directions give you something stupid? It's the homomorphism from L to L. Okay? Okay, so then you let the L vary. Well, okay, so first let me see. What's that? This is L dual, the dual of L n plus 1 times, right? So what's the dual of L? So dual of L is hom from R, L to R. Okay? So mapping into Rn plus 1 is like mapping into each of the guys. Okay? It's a product. Okay, so then we let L move around, and what do we get? Well, here, if we move around, like if L is allowed to vary, it doesn't matter this here, our bundle is still going to have a canonical section because there's the identity in here. So this line bundle, if you look at you glue it all over RPN, it's going to be the trivial line bundle. So you're going to have epsilon 1 here. Here, you're going to get the dual of gamma 1. How did I call it? I'm on RPN. Yeah, gamma 1 star, but now n plus 1 times. Okay? And then I'm going to have the tangent space of RPN, and I'm going to have an exact sequence. Okay? So here you have an exact sequence that describes the tangent bundle of RPN as a quotient. Okay? Do you guys see it? It's this modulo a trivial bundle. Okay. But now, let's see. I went below my line. That's great. I've been ignoring my own lines. I wanted to be able to write up there. Okay? So what I want to say is that, well, so you've got we have a Euclidean metric lying around. Okay? And if you remember, if you have a Euclidean metric on your bundle, then it's isomorphic to its dual. Okay? So gamma 1 n star, that's isomorphic to gamma 1 n. Okay? And also, you can use this metric to split this short exact sequence. So you can use the metric. So you have this metric here, and it gives you this, but it also gives you a splitting. So split. So when you put all these things together, you get that the tangent bundle of RPN plus a trivial line bundle is gamma 1n sum with itself n plus 1 times. Okay? So now let me say a comment. So first of all, one of you guys pointed out to me yesterday that in algebraic geometry, this is called the Euler sequence. Okay, so maybe that speaks to some of you. In algebraic geometry, it doesn't necessarily split. I mean, I'm using something really special about R here. In fact, you have, so the same story runs if you replace R by C and, you know, the tautological line bundle on C, but you're going to lose some stuff at this stage. So you're not going to have that you're isomorphic to your dual. And is the sequence going to split? No. Okay. All right. So this is preview for Dylan's talk. It also works for C. But kind of. Up to star, let's say. Up to star. Okay. Well, I mean, the star is not the red. Okay, all right. So great. Now we have a formula for the tangent bundle of RPN. And this trivial bundle maybe annoys you if you're doing real geometry, but we're doing algebraic geometry and trivial stuff. Adding trivial bundles doesn't matter. So if I look at the total Stiefel-Whitney class of the tangent space of RPN plus epsilon, well, this is trivial. So you can sort of bootstrap this exercise to check that this is going to be the same as the Stiefel-Whitney class of RPN. Okay? So if I do Xi plus a trivial bundle, no matter what the dimension, I get Xi. Okay? But now, this is the total Stiefel-Whitney class of gamma 1n to the n plus 1. Okay. Everybody agrees? I just use my equality on the bottom. But now I can use the product formula, this guy. And I use it n plus 1 times, and I get gamma 1n times, so to the n plus 1. So this is just an element in this cohomology, and I can take its product n plus 1 times. Okay? So I just used this repeatedly. Okay? Yeah.
We lost the rule when we got that.
So yeah, I just replaced here the duals with their guys. Yeah. Okay. And now this is 1 plus w1 to the n plus 1, right? Because we just computed that in the previous example as 1 plus w1. Okay. And so now we're working mod 2, and I mean, well, you can use the binomial coefficients anyways, but you get a formula to the n plus 1. N plus 1 choose I of w1 to the I. Okay? And that's the total Stiefel-Whitney class of RPN. Great. So let's check a consequence of this. So let's see. These binomial coefficients, this is mod 2, right? Okay? If n plus 1 is not 2 to the k, then you're going to have an integer I between 1 and n plus 1, which has the property that, and I think I want 0. No, 1, n plus 1, 1. Means 0 and I. 0 and n plus 1, such that n plus 1 to the I is not 0. Okay? Just check that. If you're not a power of 2, one of these things is going to be non-zero. Okay? Not 2. Okay? All right. So at least one of them. So in particular, for such an n, the ith Stiefel-Whitney class of RPN is not 0. Okay? Because it's going to be a non-zero term here. Okay? So what does that mean? It means that the tangent bundle of RPN is not trivial. Okay? So if n plus 1 is not a power of 2. Okay? So just to sort of feel it a little more, let's do n plus 1 is a power of 2. Then you get the W of RPN is equal to 1 plus W1 of 2 to the k, which is 1 plus, we're working mod 2 here. And this is the calculus, or the freshman's dream, that you can just bring in, mod 2, you can just bring in the exponent, okay? So this is W1 to the k, mod 2, okay? But now, what's n here? N is 2 to the k minus 1, okay? So h star of RPN 2 to the k minus 1, well, that's z mod 2 W1 modulo W1 to the 2 to the k, right? So this is just 1, mod 2. Okay? Do you guys follow that computation? okay? I'm just saying, so take n plus 1 to be a power of 2. Then I use the formula for the total Stiefel-Whitney class. I use the fact that I'm computing mod 2, so I pull in the power of 2. But now this class, this is supposed to be in the cohomology of RP2, and W1 to the K, 2 to the K is 0 in the cohomology of RP2 to the K minus 1. You're like too high. So then you lose it, and you only have 1 left, okay? So if n is equal to 2 to the K, so RP 2 to the K minus 1 could have a trivial tangent bundle. Okay? All right. So what we've shown is that it can only have a tangent bundle if Rpn is of the form 2 to the K minus 1. Okay? It can only have a trivial tangent bundle if, yeah. Okay, and sort of this is a deep theorem of atoms. So this is the Hoff invariant 1 problem. And it says that T of Rpn is trivial if and only if n is equal to 1, 3, or 7. Okay? So yeah, parallelizable. I can't write that, so I actually chose not to use the name. But if you guys spell it for me, I can write it. Pair, how many are? A. Yeah, I know, seriously, like I thought about this as I can't say the word and I can't write it, so I'm just gonna not say it, okay? So this is, okay, and this is related to the like Hoff invariant problem, as I said, but also like the vector field on sphere, the division algebras on our end, like it's that big problem in topology that does all these cool things for you, okay? So the Stiefel-Whitney classes didn't tell us everything, but they told us that if you're gonna be parallelizable, you have to be a power of 2. There's other ways to prove this, but here's one cool thing that you can do with Stiefel-Whitney classes, okay? Yeah.
I'm sorry if this is too pedantic a comment, but I like to think about this of these numbers as arising from the dimensions of the fibers of the Hopf vibrations.
Mm-hmm.
And so, and it would be true if we included RP0, if we were to think of such a thing, right?
Yeah, I mean, what's RP0?
Yeah, it's a point.
Sure.
But it's nice to have it all, you know, there are 4 Hopf invariants.
No, that's fine. I don't mind. Yeah.
You'd like multiplication by 2 to be a Hopfman?
Yeah, right. Because it is. It's
No,
a
it's fine.
function.
It's fine. I can add 0. Yeah. Yeah. If it makes you feel, it's okay. Yeah.
It's kind of pretty, right?
Yeah. Yeah. Yeah, no, I'm not even gonna, I didn't even try to argue. I was just like, okay, that's fine. Yeah. Okay. Okay, so let's see. So another thing that you can, so I'm not gonna have time to talk about it, but there's some exercises in there. So is you can use Stiefel-Whitney classes to study. So the question, does Rpn, so this is immerse, in Rn plus k, okay? So, or for which k can this immerse, okay?
Awesome. Remember when you guys were in kindergarten and they told you the Klein-Bell was going to immerse the power 3? Now you know why.
Okay, so there's exercises, and I mean, some of the exercises I was going to set up a little better, but what you want to use in those exercises is this. So hint for exercises. This is sort of, you want to play with the normal bundle, okay? And figure out what it tells you about these formulas, okay? Start with RP2, okay? Figure out where can you immerse RP2? What does K have to be? Or, I mean, how big does K have to be if you're going to have an immersion? Yeah. Yeah. Do you have a good answer?
Yes, but I'll tell you that.
Yeah. Okay. Okay. So let's see. Okay, great. Stiefel-Whitney numbers. We're doing good. so I'm going to keep my Stiefel-Whitney class up just a little longer. So really, really cool problems you can study with the Stiefel-Whitney classes. And if you've sort of thought about these things before, you might realize that some of these questions also, like sometimes, like this part, you can prove that with sometimes you see a proof with the Steenrod squares. Like you look at the cell structure of some CW thing, and you look at the Steenrod squares that can attach stuff. But remember, Stiefel-Whitney classes, Steenrod square, they're defined like, I define the Stiefel-Whitney classes in terms of the Steenrod square. So that's not a coincidence. Okay, now back to Cobordism. So Stiefel-Whitney numbers, AKA Stiefel-Whitney numbers. Okay? All right, so I'm going to let R1 plus 2R2 plus ... plus nRn be equal to n, and the Ri's are positive integers. Okay? So take a sequence of positive integers that give you this equation. So for example, if this one is non-zero, then you have nothing and you just have 1 in it. Okay? Non-negative. Okay. I is non-negative. Thank you, Peter. 0 is allowed. Okay. Then, okay, let's look at W1 of m to the R1 times all the way up to Wn of m to the Rn. Well, so these are cohomology classes, right? So this is in H1, this one, and this is in Hn, this one is in Hn. So if you think about it, the total, this product with the powers, is going to be in Hn of m. Yes. Yeah. So what I'm saying is, I just said that, but the point is you want to look at the monomial. You have these Stiefel-Whitney classes, they're elements in your cohomology, and you want to look at all the monomials that land you in Hn. Okay? So these are the monomials that will land you in Hn, involving these guys. Okay? And why do you want to land in Hn? Because you have the fundamental class and you can pair with it, okay? And you can get numbers, which is way better than cohomology classes. And you know what's better than numbers? Numbers modulo 2. Okay? So we're going to let W1, R1 up to Wn, this is just going to be a shorthand for m, to be equal to the pairing. So I'm going to take W1, R1 of m, this class, Wn, Rn of m, paired with the fundamental class, okay? And I guess now I have M an oriented. No, wait, I'm making mod 2. Isn't that great? But M's like the, it's a smooth manifold, closed. Okay? Well, you're going to use something different. But also, like, these classes are defined in the mod 2 cohomology, the Stiefel-Whitney classes. So, like, right away, you're already in the mod 2 world anyway, so you might as well take care of it. But there's tons of generalization on Stiefel-Whitney classes and stuff like that. Okay, great. So for any such sequence, I get a number. So to a manifold, I get a sequence of numbers, okay? So I have one for each of these monomials, and they're just like 1 or zeros, okay? So it's just some, I'm sure you guys can count how many of these there are for a given n. And this is now this is a kick-ass fact. Okay, but I can't write Pontryagin either, but I'm going to try. Well, so Miller-Stasheff has Pontryagin for one direction and Tom for the other. So I'm going to say Pontryagin Tom, and then you can argue with Miller-Stasheff. Maybe I'm wrong, too. I don't remember things well. Okay, so M, right, this is too good to put solo that nobody can see. M is a boundary. So maybe I'll say it this way, is the boundary. M is the boundary of an n+1 dimensional manifold, smooth, just decorate things accordingly, if and only if all of its Stiefel-Whitney numbers are 0. Huh? Thank you, Tom Pontryagin. What a beautiful theorem. So cohomology mod 2, that's something you can hope to compute. So you have a set of numbers that you need to compute, and you compute these numbers, and it tells you whether or not your manifold is a boundary. Okay? But this also, you could phrase it a little differently. You could say, so, nope. After I'm done talking. Either, and you can mention it, okay? Yeah. So corollary, so M and M prime are cobordant if and only if they have the same Stiefel-Whitney numbers, have equal Stiefel-Whitney numbers. You guys see that? So the picture is, that's the boundary. Okay.
Earlier, if I recall correctly, said that Cobordism accounts still work with other things.
To what?
One all the way around Cobordism.
Okay, so maybe this was like the thing, like, you know, you want to understand stable homotopy groups of spheres, and maybe you compute Cobordism to understand it, one from the other. Yeah. So what do we learn more? Probably we learn more from knowing something about the stable homotopy groups of spheres and applying it to Cobordism than the other way around. But it was designed to go the other way. Yeah. I think, is that right, Peter? Did I say it right? Yeah. Yeah. Okay. Peter, if you can say Wu's formula in 30 seconds, you can do it now. What you wanted to say.
30 seconds. There is a formula depending only on the homotopy type of the manifold. Tells you if you know the cohomology of the manifold and you know its C-naught operation, then there is an explicit formula that tells you the Stiefel-Whitney classes and therefore the Stiefel-Whitney numbers. Therefore, if two manifolds happen to be of the same sex, happen to be homotopy equivalent, then one is cobordism 0 if and only if the other is cobordism 0. And you can tell that without any geometry whatsoever, just through a calculation.
I think it's cool. So
It's an amazing, amazing consequence.
I knew what you wanted to say, so that's why I let you say it, because it's cool. Yeah. No, but okay, so let's say Peter said you have your Stiefel-Whitney numbers. There's a formula for it in terms of C-naught squares and something totally topological. So that means that the right-hand side only depends on the topological structure. So, and this is telling you something about the geometry. So topology gives you geometry. Yeah. Yeah, it's Wu's. It is inconcise. Wu's formula. Okay? Great. Cool stuff. Let's see. Okay, so you know when you learn complex analysis and you're like, wow, this field is so beautiful. Why am I not a complex analyst? Everything is so perfect. I feel like this part of algebraic topology is this analog in algebraic topology, like this story. It's just everything lines up, everything's perfect. And, you know, it doesn't last very long, but Yeah. All right, so let's see. I want to give you an idea of how this goes, the proof of the Pontryagin-Thom theorem, or Thom, or whatever it is. Okay? So, all right, so we're going to look at W, an n plus first dimensional manifold. And then the boundary of W is our n manifold M. Okay? And the first thing I want to do is convince you that if we're in this setting, then the Stiefel-Whitney numbers of M are 0. Okay? So that's like the easy direction. Okay? So what do we have? So if you have an orientation on W, well, it induces an orientation on the boundary. Okay? So we haven't really defined orientation properly, but let's say if you want to say this in terms of topology, you're going to say, yeah, well, everything's mod 2. Yeah, yeah. We're all mod 2. Yeah. So you have, what's an orientation on a manifold with boundary? It's a class in the cohomology of the manifold, in the homology of manifold relative its boundary. So I'm going to stop writing Wm. I'm just going to write M. Okay? So an orientation on this manifold is you've got W. Here's going to be my picture. W and M. Okay? Is a class in this cohomology group. And n plus 1 is because W is n plus 1 dimensional. Okay? Homology. Yeah. So it's a choice. So yay, no choice. Okay, so it's the non-zero element in here. Okay? You can prove that this group is going to be Z mod 2, and it's the one guy that's not 0. Okay? And what does it mean topologically that this gives you an orientation? If you take the boundary homomorphism, okay? So remember, you have a long exact sequence. This might come up. So Hn plus 1 of M goes into Hn plus 1 of W, goes into Hn plus 1 of the pair, and then you have the boundary, Hn of M. Okay? And for this orientation to restrict to the boundary is the same as saying that this maps to a fundamental class, an honest fundamental class in here. Okay? Do you guys understand the statement? Okay. So you have this beautiful formula. Del of W is M when you're in this setting. Okay? All right, so what's sort of a, I don't want to give the formal definitions, but let's see, what's a sort of vague idea is, okay, we have talked about cohomology, homology in various ways, but suppose you were doing like a singular, what's the one where you cut up in triangles? Simplicial homology. So you cut up your manifold into triangles, W, you cut it up. And then, you have a bunch of little triangles, and you take their sums in your homology, like these triangles, they're cells, and they generate sort of the thing that you use to compute homology. You take the boundary, well, the boundary is going to land, so everything that's outside, everything that's up there is going to sort of cancel out, but you're going to end up with a cut-up version of the boundary M. So you're going to have a bunch of triangles that are going to be a triangulation of your manifold M. Okay? And this fundamental class is exactly that class where you take all your triangles and you add them up and you look at the cohomology class it gives us. So you're just saying that this cohomology class, this relative cohomology class, when you take its boundary, gives you this cohomology, this homology. I keep saying cohomology, but I mean homology. Yeah.
So this is sort of unremarkable Z mod 2, so are you saying this is in the middle of Z mod 2?
You're right, this is unremarkable for Z mod 2. Yeah. Okay. Great. So that's okay. I have enough time today, so I think we're good. Okay. So now I have my manifold. W, okay? And I look at a collar of M. So I should have drawn it differently. I want it to really look like a collar. So I have M, and there's no corners, so I'm just smooth it. Okay. Okay. So I've got W, and I've got M, okay? And I've got my collar neighborhood. Okay? So along the collar, you can see that there's a vector field, an inward pointing vector field along M. Collar.
Okay.
Yeah, yeah. Okay. So if I look at the tangent, do we have color? Color. I didn't do it. I'm gonna let you guys. So you have the so this is the tangent space. So here in red is the tangent space of W restricted to M. So in other words, so I have a map I from M to W, and I take the pullback of the tangent space of W. And Dylan wrote it yesterday as the tangent space of W restricted to M. Okay? And if you look, I've got this vector field pointing outward along M. So that means that in this, I get a copy of a trivial bundle. Okay? It's just this. You can see it in the inward pointing vector field. Okay? So this is going to be the tangent space of M plus a trivial line bundle. Okay? You see the other, what's left if I get rid of this, the orthogonal complement, that's the tangent of M. Okay? You guys see that? So the tangent space of the big manifold restricts to the tangent space of M plus a trivial guy. So in particular, if I look at the total Stiefel-Whitney class of this, okay, of the pullback, that's, well, we don't care about trivial bundles, so that's W of M. Okay? Okay. So, but we have naturality, so that's the pullback of W, and here I'm going to drop the T of big W. Okay? All right. Okay, you see this formula? So if I pull back, this is like now the map on cohomology induced by this map. And if I pull back the total Stiefel-Whitney class of W, I get the total Stiefel-Whitney class of M. Okay? So that means that this is true for all of my Stiefel-Whitney classes. Okay? So I can look at my Stiefel-Whitney numbers. Okay? So I can look at W1 of R1, Wn of Rn. So evaluate on M. Okay, so by definition, this is W1 R1 of M dot 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 Wn Rn of M paired with the fundamental class of M. Okay? But now I'm going to use this. So each of this is the pullback of the thing for W. And I star is a ring homomorphism. Okay? So that's the same as saying I'm going to pull back the same thing, but for W. Do you guys agree that this line is the same as that line? You're right. Now? Okay? But now I'm going to, we have this formula, so we're going to feed that in. This is the boundary homomorphism on the class of W. Okay? Now you're going to have to convince yourself of a general fact that if you have a map F from X to Y, then you have the map F star on cohomology from Y to H star of X. And the fundamental pairing has the following property. So if I pull back a class alpha and I pair it with a class A, that's the same as doing alpha and doing the map on homology to A. Okay? And now maybe A alpha is in H of Y, and A is in the homology of X. Okay? Okay? So I can sort of So the pairing is going to respect like using the map on homology and then pairing and or doing the opposite. Okay? So just, check. All right? But that means I can move this to the other side. So this goes here. So I get W1 of R1, W dot 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 Wn of Rn, W, and I pair it, and then I do the push forward of delta of M. Okay. Thank you. But now, okay, so I'm going to hide this for a minute, not even a minute. Yes, erase my 1, and then I'm good. Or do this. Okay, so the map is the inclusion of M into W. That's the map on homology. That's the map that appears in that sequence. This is an exact sequence. If I do one and I do the other, it's 0. So in particular, this and then that's 0. Okay? So this whole number is 0. Okay? Does that make sense? What's next? It's this. Yeah, it's a Cobordism. I mean, of course, Cobordism, we saw that lots of things were Cobordin, especially in the unoriented. Remember Jolie's introduction, n is equal to 1, there was only a couple things when there was a lot of manifolds. But sort of this is we know that Cobordism is sort of not a super strict invariant, but it's pretty good. Exactly, yeah. And remember, if we just use the total Stiefel-Whitney class, no, I'm not going to say that. I have nothing to say. Okay. But yeah, so that answers your question, right? Okay, yeah. No. No, I'm looking here.
No, the second and third line, right near there.
Okay, am I pointing?
Go to the right.
Right?
Then go down 1.
Yeah.
When you're plugging in towards W, that's
No, I'm not. This is the nth. So it's so this part doesn't change, right? This is just a cohomology class.
okay.
Okay, and I'm pulling back. So
If right above W should be N.
Oh.
So W. Oh, no.
I think there's no mistake. Yeah. No, but whatever. I want to answer his question. If you were confused, then that's so yeah. But I think this is right. But what I'm saying is that you have, just think about it in terms of, I have a cohomology class like this, and I have a map. So I'll just use I star again. So I have this in the cohomology of W. Well, so that's all I'm doing. I'm just okay, so this is what Peter's trying to say. He's saying the line above your head here. But, the point is, the way that I wrote it, you could put an I on all of the, I is a bad letter. R, okay? So, yeah, does that help? So I have one WR or RK, it's a class. WRK of M, it's a class in the cohomology of W, or whatever. This is a class in the cohomology of W. If I pull it back, I get that one. Okay. So then plug this equation with all kinds of powers and using the fact that this is a ring map into here, and you're going to get that. Okay? No, sometimes it just, yeah. Oh. Yeah. Guess that may, yes. Yeah. Yeah. Good eye. Yeah, I guess that's true if you're, yeah. Okay, everybody good with that? Okay, so the other way around. So I wasn't too worried about getting here, but so now what do we have? That if the steeple-Whitney numbers are 0, then M is a boundary. Okay, but we also have that if the steeple-Whitney numbers, yes, we did. But on my notes it says now I want to do the other direction. So we want if your steeple-Whitney numbers, so we now want to show, but we're not actually going to show all the details, but then M is a boundary, is equal to del W, okay? But we have, and we can use that if, so we've proved that if M is a boundary, then the numbers are 0. Okay? So, but that gives us this corollary in if it gives us this part. Okay? Right? Yeah, I got my implications right? Yeah, great. That's never trivial. Okay, so then oh no, I want to keep that for just a second. If. Okay. Okay, so now, okay, so remember we have this, so we've called it this and we've called it this in the lecture, just different scripts, okay? So it's the group of, Cobordism classes of manifolds, okay? Now, what have I done? So we have, remember that we have H star of BO is the cohomology of the union of all the Grassmannians. K is greater or equal to 0, the Grassmannian K of R infinity. And this is supposed to be the ring that knows about all the steeple-Whitney classes. Right? It's a polynomial ring on infinitely many generators, which are the steeple-Whitney classes. Okay? So now, if I have Hn of BO, it's in here that these monomials live, right? These monomials, they live in here. You guys all agree? Okay. The RIs are picked so that this monomial lives in here. Okay. And this cohomology doesn't know about sort of the higher monomials because they have too big degrees. Okay. But great. Now I can look at this tensor N, the group of Cobordism classes. So if I take a manifold and I take a Cobordism class, I take a representative manifold, then I can get a map, which is the steeple-Whitney number, and it goes to Z mod 2. So it sends one of these guys, so W1, R1, Wn, Rn, tensored with a representatives for my, so you have just a Cobordism class now. Cobordism class, not fundamental class here. I know, confusing. What are you going to do about it? I guess I'm going to do something. Cobordism class. Great. Okay. You guys get it? I just didn't want to use the both brackets. And you can evaluate it. So you can take the steeple-Whitney number. So W1 of R1, Wn of Rn of M. And it doesn't, so the reason why I'm belaboring things is that this doesn't depend on the representative, right? Because if two manifolds are cobordant, so if they're equal in this ring, they have the same steeple-Whitney numbers. So this is a well-defined map, okay? If any of the, so this is just, so if any of the, I mean, you could have one monomial pairing with the manifold and giving you 0. You can have some of the steeple-Whitney numbers to be 0. Yeah. You fix, so now I'm looking at all of them. If you fix one of them, you get a function on the n.
Right, okay.
Yeah, okay? But I'm allowing it to vary. Like it's just like, I have an element for each of these guys, and for each of these guys, I can form the pairing and tell you an answer. Yes, you're not. No, this is the most beautiful group ring field set. Well, no, there's better sets, but but this guy's pretty good. Okay. All right. So you guys understand what the map does? Okay. And now the point is, so this makes sense, but now we're going to use stuff that Jolie said. Oh no, I want to say I want to say one thing. Okay. So what happens if all of the Stiefel-Whitney numbers of a manifold are 0? Okay. So suppose that I fix M now. So we're used to fixing this, but now fix this. And suppose that no matter what you plug in here, you get 0. That's the same as having all your Stiefel-Whitney classes numbers 0, right? Okay? Well, that means that you have and now suppose that M is not 0, so it's not cobordant. It's not a boundary in here, okay? So M is not a 0 element. But all of its Stiefel-Whitney numbers are 0, it makes this pairing singular, right? That's what it means for a pair or non-degenerate, or degenerate. You have a non-zero element that pairs to 0 with everything else, okay? So if our theorem is not true, then this is a singular pairing, okay? Because there exists some non-zero thing, all of whose Stiefel-Whitney numbers are 0, okay? Logic clear? All right. So now the point is that the point of the proof is that this is not a singular pairing, okay? This is the proof that Peter gives in his book. It's, did I say something kind of wrong?
I don't know.
It's fine. Keep going, keep going.
Okay, well, I want to get corrected because then I'll learn. So let's look at this map. So you have the map N, this guy, and there's a map alpha, which goes to pi n, and now you guys, so pi n of TO, which is pi n of MO, okay? Yeah.
Before you do that, can we write the map from N, the adjoint of that map? The map from NN to
Don't do that.
TO. I just want to ask a question.
Yes, you can answer your question, but you might be the one that answers it.
I think we're about to show something about that map, but that map's not an isomorphism, right? I believe it's
What?
just an injection.
That's going to be fine. That's fine for the proof.
I understand that it's fine. My question remains.
So is it in my language? All I want to say is that, so Dylan, I want to prove that there is no non-zero guy here.
Everything
Yeah.
you said is fine. My question was an actual question, not like a...
No, I understand, but I don't understand the question.
So that's why I wanted you to write down the map, but Peter didn't want you to write down the map. Because otherwise my question makes no sense. My question is the adjoint of that map an isomorphism? I know it's an injection, it's an isomorphism. Great, that answers my question.
Okay.
I wasn't trying to be...
No, I didn't think you were. I just didn't, yeah, okay.
I have a question as well. Sorry, the non so you said the non-zero meant if like the Stiefel numbers were 0. I don't see how that's possible.
No, I'm saying if so suppose you have a non-zero M and you assume that all its Stiefel-Whitney classes are 0, then maybe let me write what I'm going to write, and then maybe we'll fix my language. Okay? So maybe I may be saying something wrong, okay? So now Jolie talked about this map H, which was so what is this? This is the Pontryagin-Thom isomorphism. This is the Hurevich homomorphism that Jolie was talking about, and this goes in H n of MO, which is TO. Which one do you guys like better? How's MO? MO, yeah. Sorry, Peter. Okay, and then you have a map to H lower n of BO, and this is the stable Thom isomorphism. Okay? So this one is an isomorphism, this one is an injection, and this one is an isomorphism. Okay? So Jolie didn't say it, but this was part of his proof. Okay, so you're going to have to just take that for granted. So maybe you did, I don't know. Yeah, actually you did. So this map here, the Hurevich homomorphism, is an injection, and the other ones are isomorphisms. So I can call this composite H, okay? And now the claim that I will not check for you, but is that if you look at H star of BO, I'm going to give myself more space. Okay, so I look at Hn of BO tensored with this Cobordism ring, and now you can make this map 1 tensor this map H, okay? So where does it land you? Hn of BO tensored with now wherever this guy goes, which is H lower n of BO, okay? And now you have a pairing. This is just the usual homology, cohomology pairing. And the claim is that this commutes, okay? So you have an injection here.
For the diagonal axis,
Okay. So this injects into here. This pairing is non-singular. I think I can say that now. Yeah, I mean, I see what you're saying, Dylan. I think it was just my language. Yeah. And okay, so the logic of whatever I was saying, okay, so what I was saying earlier, I guess all I wanted to say is that there cannot be a non-zero m which pairs to 0 with everything, okay? Because this whole thing injects into something, and then you do the non-singular pairing here, and here you know you're not singular. So you know if you're picking something non-zero there, it's not going to pair with everything as 0, okay? But you know that this diagram commutes. So computing these values is like computing them there, and there you know that this badness will not happen, okay? And I guess the problem is with my word pairing. Is that?
The word non-singular.
Whatever, okay. Okay.
This is great.
Function. Great, okay, so I think I'll just stop, yeah. Yeah. And if you want the details of like why does diagram commute and connect it with like Jolie's talk, chapter what, 25 of Peter's book, Jolie? Chapter 25 of Peter's book, section 5 of chapter 25. Yeah. Questions? Yeah.
From, with that, point out the card number don't depend on, what, but you still have to map from pi n and then let's go, has triangle photos and therefore, essentially two sides.
Therefore, just repeat the last sentence.
Therefore, when you tensor with cube,
Okay.
it's then, over here, is, basically, every time speed is somehow you could have gotten away with that, without, somehow you could have gotten away with without doing the first step.
Oh, without doing the first step? So he's saying, could I, so let me just say what the question is could I have gotten away without doing the first step?
The first step is also
Yeah.
a consequence of the commutativity of that diagonal. So here.
But to define this map,
Well, right, so what you do is
so you do
you define the,
like manifolds or whatever?
you say do the horizontal and then vertical arrow.
Yeah.
And then you check that indeed that can the proof that this is one.
Sure.
But it's the same proof. So
Yeah.
it's not.
Okay. So maybe.
The other proof is so simple.
Yeah. Yeah.
And historically, came several years
Yeah.
before. There's a paper, I think it was 1962, that raises the question, is the converse true? And 2 years later, there's this unbelievable paper before that everybody agrees. It's just
This is the one Ina mentioned, right? Yeah.
totally recommending it. It's just aching with you. So that's it.
I guess we can put it on the, we can put a link on the website a link. Yeah,
And you can choose to click on it or not.
it's up to you. And it's not our fault that the other people who have that link it to something else. We're just saying one can go to this website. I'll put it on the website. What is the name? It's 1954, Tom. Variété différentielle. Variété. And now this is where like my French is on camera bad. But we might find a link to the English version. Ciel. Okay. All right. Other questions? Yeah.
You never said that if the Stiefel-Whitney numbers is 0, then the class is 0, right?
I never said that when the Stiefel-Whitney numbers are 0, then the classes are 0. These guys? Or which
Okay,
one?
Is it possible to have all 0 Stiefel,
Mm-hmm.
but the class is not?
Yeah, what do you... Okay, wait, what do you mean by class? Let's just clarify that because the question depends on it.
Stiefel-Whitney class.
So, oh, okay, so you have all the, yeah. Take the RP odds. Yeah. Yeah. Actually, great exercise. Yeah, so just check, yeah. Okay. I mean, this was Jolie's talk. It was non-trivial. Yeah. 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 So can I just pause you? Can we talk right? Can I let everybody else go and you and I will talk? Okay, so let's stop. Let's take a break. Yeah.